Okay, let's use R to practice support vector machines. We're going to look at various parameters that you could use on support vector machines and how to find the model the system produces, and also to see the effects of selecting different parameters like the cost or the gamma, how about that going to affect the performance and using different kernels. So we need a set of packages, and some of them are for plotting. So I have already called those libraries, and we're going to get our data. Well, as we probably suggested multiple times already, feature selection is a key thing in machine learning, especially non-artificial intelligence, non-neural network methods. And so for support vector machines, feature engineer also make a difference. It can make a difference. But in our case, because we know that the features that we have, they're not really very informative. Besides age, all the other parameters are not very informative to predict the race. So I did actually try different combination of attributes. So select certain attributes and run the model. And it turns out the impact of those features were not great. So if I only remove the ID, well, to remind us what's in shooting data. So here are our attributes or our features. So if I just remove the ID, I got a performance of 0.61. And I also run the risk of overfitting because the test on training example is actually 1. So that's definitely not very good. So I removed ID, name, dates, and include all the rest. I have a performance on test data. I have this, and on the training examples, I have this. So this looks reasonable now. Because whenever you have training example have a perfect score, that means that it's a strong sign that the performance was overfitting. Having features that's probably too many, that you have projected data into such a higher dimensional data that it's trivial for you to find the best segment push partition to put your examples into classes, but they don't reflect the real model. I mean, it won't address the real problem. This one is not your real performance. It's just because that you have too many features for your for the number of the data observations that you have. And I also removed a whole set of things. ID, name, date. So those are high cardinality attributes that I don't believe they contribute to the race distribution. So I removed them. Armed, I prefer armed, grouped armed. So I removed this. Age, we have grouped age. VP ratio has not been found to be very useful. And we have the discretized VP ratio. So I use that. I removed this. Year, month, all those attributes were removed. After I removed those, the model has a very similar performance when I keep them. So this says, as I think we talked about this multiple times, we always prefer a simpler model. if we can use smaller number of features to achieve the same performance on the training examples, here, the training example up here first. On the training examples, then we rather use the simpler model. If I further reduce the number of the attributes, I just keep age, race, population level, poverty level. Those are the attributes that we gathered from our decision tree exercise. And those are the most informative attributes. If I only keep them, my performance dropped on both test data and training example. Therefore, we can see this is underfitting. So I'm going to stick with this choice for our rest of the demonstration. Again, don't expect our performance to go really high. 61% is probably the highest we can go with this data set. So now we have our shooting data collected, attributes selected, and we want to remove all the rows with NA because this implementation that we're using now from the package of E1071, this is the support vector machine package. This support vector machine does not handle missing values, so we will remove all the rows that has a missing value. And then we will have to convert all the character attributes. So you can see we have lots of characters here. So those are character attributes, character. We need to convert them to factors. This is also required by this support vector machine algorithm. And we use the attribute string as factors to first unclass this shooting data and then repackage it as data frame and use these attributes to tell the system to convert all the characters as factors. So this is going to convert our character data type into factor data type. So we can check on that. So you can see, oh, now we only have numerical. Logical is considered numerical, numerical and factor attributes. Okay. So now we're going to start to build model to split the data. So we will have our first use set seeds to make sure that every time that our results are repeat the result that we obtained from the last run, because we're doing sampling, right? So yeah, set the random seeds and divide our examples into the sample is going to hold 80% of the training examples, and the rest of it, which is 20%, the negative sample, going to be the test. So this is how we're going to do the train and test split. Now we can use the method support vector machine. And first of all, we say that we want to use all the variables in our dataset to predict the race. And our data is the training example. We want to use the train. We're going to first use the kernel, a linear kernel, and we're doing classification task, not numeric prediction. So type is classification. We set cost to be 1, and later we're going to look at how this cost parameter is going to affect the performance. Non-action is omit all the NAs. So this creates a model, and then we again, just like what we did before, we have a score function. This computes the accuracy. We have explained this multiple times before, so we don't have to do it again now. So we have the score function, and now we can look at the model. The model says, okay, you are predicting 6 levels, so Asian, Black, Hispanic, white, and other. a Native American, I think. Number of support vectors. So we want to, so remember support vector machine is a binary classifier, so it only classifies two classes, but we have multiple classes. The method that we use here, this method is the package in E1071 does pairwise, one against one training for multi-class classification, which means that there is one support vector machines trained for each pair of classes. So therefore, we have this many binary classifiers trained. So K is the number of the classes that we're interested. Then we're going to see later that the final decision that the support vector machine make is by a voting scheme to take into account all those binary, the result from all the binary classifiers, this many binary classifiers. So we see here we have number of class to be 6. We actually build 1, 2, 3, 4, 5, 6. 6 classifiers. And this, correct myself, this is not, this is the total number of support vectors. And here for every class, the number of support vectors for every class are listed here. We go into the cost is 1, which we give it here. And we used the classification mode and we used linear kernel. So we're going to actually look at more detail in the model that's produced using a simpler example, because we currently have this 6 class that's going to produce 15 binary classifiers. It's too much to look at. Shortly, we're going to look at a simpler binary classifier example. Then that will be easier for us to examine the model that's produced. So right now we actually have a model, and we can use this model to run on our test dataset. See, the performance is around 60% accuracy. And now we have, if we run this model on the training example, of course, we used this model we used the training example to train this model. We will never report this result as a performance score. I'm just using this to assess the overfitting potentials of overfitting. So we run this. We can see in general, the learning algorithm is going to work better on training examples than test. But shortly, we're going to see another example to show you example of underfitting, where the performance is actually better on test than training. But here, what we see is pretty normal. Training examples, the performance on training is better than the performance on the test. So why you ask why training does not produce 100%? That's it because we have this cost, right? We accept some error and we give it a cost parameter to see that we want a soft margin. So next we're going to see some parameters, our choices, the hyperparameters that we choose. So let's make it more clear. Hyperparameters. So again, it's the same data set. We don't need to do all of that. But what we currently do is going to try out different kernels. And as you can see, support vector machine can do the cross-validation for you using our data. So right now I'm giving it the entire data set and have the system to do cross-validation. So in this setting is pretty much similar to what we did before. I think the default cost is 1. Let's check. Let's look at what's the cost. Default cost is 1, so I did not specify here cost is 1, but it is 1. So we're going to run this using pretty much the similar settings, but using different kernels. So we can see this model gave us accuracy. Oh yeah, this cross-validation 5, it's going to take some time. I'll pause my, the result comes back. So we ask the system to split the examples using 5-fold cross-validation. So we have 5 runs performed and the 5 accuracy results are returned. So those results are comparable to our results earlier. That's because that we did pretty much the same thing, right? So at least one of the value was exactly the same. But I want you to observe that when you run this 5 times, your performance actually can differ, and sometimes it differs quite a bit. From 57 to 61, this 58 to 61, that's 3 percentage point. In some machine learning articles, what you're going to see is that 3 percentage point of performance increase might be even significant. I often cast my personal doubts on those data, so that's why we always need to do t-test. We always need to run the algorithm multiple times to figure out exactly what number is more representative of the algorithm's performance. Okay, so we got linear, and now let's run redo. So at this time, I'm just picking those most common parameters, and later we're going to see how to best tune the system, select best combinations of the parameters. Again, it's going to take a bit of time. Okay. So what we see here, we have some 62, seems to be better, but we have 51, 55, which is lower. So as you can tell, it's not very easy to directly compare the performance. That's why we need statistical tests. And run polynomial and the sigmoid. I don't have to run this through, right? So polynomial, I just want to point it out. You have another parameter, degree, whether it's cubed or squared, you know, what's the power that you want to use over there. And the sigmoid, the result on this data set, given our random seeds set to be 1, sigmoid gives the worst performance. But that's how we do compare different kernels. And next, I want to show you that support vector machines also give you a parameter class weight. So it uses information to adjust a certain algorithmic aspect, so that you tell the system that in my class may distribute this way, and it reflects the true distribution. So based on the weight, so this is how I computed the weights. So total number of this is total number of observations, and the divided by number of the occurrence of different rays. This basically is an inversed proportion of the race distribution in our dataset. This can sometimes help support vector machines to adjust a certain parameters, the algorithm sets itself. But in our case, telling the system the weight did not help. This could also be used when the class. So currently, our computation weight basically tells the system that the weight our data reflects the true distribution of the race distribution, which is not true, right? So if we have the real data there, we actually can provide the class weights here to tell the algorithm in the real population how those different races are distributed. But running this model, giving the weight information did not change our performance. I think it made the performance worse. And this is very typical. Sometimes you think, wow, I found a new piece of information that might actually help the algorithm. It turns out not. Yeah. So that's why a lot of times people can't tell you how to do. You have to try different ways to improve the system, improve algorithm performance. In other ways, sometimes, unless you have lots of experience, have similar data, it's often difficult to predict exactly whether a piece of more information going to improve the performance or drop the performance. Okay, so now the next topic I want to talk about is tuning. So support vector machine requires you, the designer, the data miner, to tune the model to get the best combination. So we will use this tune method to try out different kernels and use different hyperparameters. And then the system can, after the tune out result is provided, you can actually find the best parameters and the best performances. This takes a long time. I will not be able to run this. It's going to take hours. So let's see. I have a simpler example. Let me first start to run it. And then I'll explain what I'm doing here. So here I'm trying to find best combination for linear kernel. And here it's my tune control. So here the range, the list, is the parameters that you want to test out grid search, remember? So you can do a very systematic search like we did, that we write out earlier. Cost can be a number, a long sequence of different possibilities. Gamma can be a long different sets of values. And the degree, why do we need degree here? Oh, we're doing polynomial, right? So we need degree. So every combination is going to produce one support vector. Well, if you have actually binary classifications, if you have multi-class classification, you're going to produce lots of classifiers. What I'm saying here is each different combinations of this value are going to produce a performance estimate. And then you will be able to find out whether the cost need to be 0.1 and the gamma should be here and the degree need to be 4. Maybe that going to produce the best performance. Okay. So here, in order to simplify, to make the system run a little bit, to make this video shorter, I have to just try out kernel, linear kernel using just very simply cost. And I also used the tune control thing that you can also control. Sampling method, you can use cross-validation or bootstrap or make fixed held out cut. Number of boost strapping, I set it to be 10, and it's regularly to be in hundreds and 500s because I want to keep this video short. So I used a very small number here. The boot size is how you want to divide your training and test samples. So here 80% of the sample are randomly selected with replacement as the training example. Okay. So we have this tune out complete, and now we can look at this is what we ask the system to do. The best performance is not very good because, we used linear limited to this. So among those different settings, our best performance was this much. We used bootstrapping, and now you can actually have the system to tell you what's the best parameters. So cost the system, compare between this and that, 0.01 is a better parameter. So you're going to choose that. You can also ask the tune out to give you the best model. So here we have the best model is to given our parameters. The choice is linear and this use cost of 0.01. And we have collected this, over 3,000 support vectors. So as you can see, we have too many support vectors. That's a problem. Another performance estimation method you have practiced before. It was coming from the book. I have tested this method multiple rounds in different datasets. I have found that this method is not bug-free. So the major issue is it will not reliably and correctly split some of the training examples when you have those. So luckily for support vector machine, you already have the package already gave you those tuning methods that you can use. And we also introduced by hand code our approaches to collect results from multiple models in our decision tree examples. So I'm not going to run this performance estimation again. Now, so as I promised earlier, I'm going to use this a smaller dataset to examine details of this model, what this model return. So we're going to use our classic ARIS dataset. So here, simply we just use whatever attributes there to predict species. This is exactly the same way as this. We're just using different ways to tell the system to make the prediction. One is using this model, the other is listing the attributes and its labels. Okay, so we're going to run this. Let's first see ARIS. And we run the model. So for default kernel is radio, and with default cost is 1. I think we have seen that before. Number of support vectors we got was 51 for this small ARIS dataset. If we do a summary of the model, I think we're going to see the same thing. But we can look at, well, we can run the summary of the model. Yeah. So we have 3 classes, and for each class we have this number of support vectors, and the total number of is 51. We have 3 classes, so there's 3 species we want to classify the observations into. So look into the models. The model returns the mathematical formula and how the system makes decisions. So I'm going to explain those. So 50 support vector, it will tell you 51 that we already see. So the number here is the original observations. So those observations turn out to be support vectors. Okay, so here we have this many support vectors. Okay, so each support vector, as you can imagine, is projected to as one dot in that multidimensional space. And index, again, it's just repeating what we have here, 9, 14, 16, 21. So it tells you which, the index of the original observations that turn out to be support vectors. Okay. And then the coefficients tells you this term, the ATJ times YTJ in the decision function. If we go to our, up here, so here, this is the coefficiency. So for each support vector, we have a coefficiency term. So using that, you can actually construct this formula. And we also have B. B is rho. So rho is the B in the decision function. And the NS total number of support vector machines that we just saw. So let's bring out those rows. So we have 3 B's, right? Because we have 3 classifiers. Oh, because we have 3 classes. Right, because we have 3 classes, right? So let's now look we look at the model, what's inside it. Now we can use the model to predict our data. So those are the petal width and petal length data. And we get the prediction, and we can check the accuracy by compare the prediction with the real value y. So here we have put y into the species, the gold standard, the real answer in the y, in variable y. So we can do. So what we see here is we want the values on the diagonal line to be greater. Those are the correct predictions. If we see lots of numbers off diagonal, then we are in big trouble. So now I want to show you that when we ask the system to show us decision values, we can actually make sense how the system made the prediction. So, and run this, have the system to display all those values that's being used for prediction internally to the model, right? So those are the. So first we see here that the support vector machine, this implementation does do 1 against 1 classification. So this is one support vector machine. This represents a second support vector machine, and this is the third support vector machine. Every support vector machine classifies between 2 classes, Setosa versus versicolor, Setosa versus Virginica, and versicolor versus Virginica, right? So then those values are the decision values. So if the value is greater than 0, then the label, the system is going to choose the first class as a label. If we go down further enough, we're going to find some values that are negative. If those values were negative for this case, so the case 51, the system going to predict the second label as the label for that observation. So for case 51, the prediction going to be this support vector machine's prediction going to be versicolor. Okay. So that's about the prediction. We can also visualize our examples. We can see that we are so familiar with this ARIS data set, we know they're separable. So those plus signs are the support vectors. You can see there are support vectors for the black class, support vectors for the red class, support vectors for the green class. So those are the 3 groups of support vectors that made up the 51 support vectors that we saw earlier. The last point I want to make is that you can actually have, instead of returning those decision values, you can also ask the support vector machines to actually produce probability. So let's run this using probability, our prediction. And here we can look at the attributes, the probability values for those decisions. So here I only show the first 6 rows. So for Setosa, the first observation has a very high probability being predicted as Setosa, and have lower probabilities being predicted to versicolor or virginica. Therefore, this Setosa going to be the one. Setosa going to be the label for the first observation. So earlier, what we see here when we use not the probability but the scores, what we see, because this is greater than 0, so the first support vector machine going to predict Setosa. This is also greater than 0, so second support machine will also going to predict Setosa. The third support machine going to predict the versicolor, but the 2 out of the 3 support vector machines predict Setosa, so the final label for the first observation going to be Setosa. Okay, so this video is getting really long, but this is the very last point that I want to make, is the test out the effect of cost and gamma onto classification problem. So it's a binary classification problem. So in this case, it's easier to examine one support vector machine instead of a set of 6 or 15, right? So in this case, what I did is to get our shooting data. So using the original have lots of attributes. The reason that I switch back to this original data set is what I want to show you the result that match what I have in the lecture notes, so you don't get confused. So I have this NA removed. I convert characters to vectors. I dropped any levels except the black and white. Okay, so I only keep those 2 classes. And here again, this is our score function. I don't think we need to rerun this, but well, let's just do it. Again, split the samples. So here I'm use the radio kernel as the example to show the effect of cost and gamma. So earlier we have discussed the bias and the variance in the lecture. So if you have a bias, if a model is highly biased, that means the model is too rigid. It's not flexible enough to fit the data. So a high bias model often is underfitting the data. Variance refers to the model's flexibility. Model with high variance is very flexible, and it can twist in whichever way that you want to in order to fit the training example. So high variance results in overfitting. Okay, so I'm using this to illustrate the effect of gamma and the cost, these 2 hyperparameters. When we have smaller gamma, the decision, remember the gamma is kind of like mountain hills. The mountain are very short and spread widely, so it does not twist itself to fit the data points, so it has high bias. High gamma case, you have those very pointy, very edgy mountain tops, so that you can actually cut the mountain in whichever way so that it fits the data better. So high gamma will result in overfitting. Smaller cost will allow more errors, because cost, having those errors, the cost is very low, so the system have more flexible to make mistakes, allow more examples in the middle of the street. So the smaller C going to result in a high biased model, where the model accommodates lots of errors. So that I'm happy having this very rough or very spread it out edge, even though there creates errors because cost is low. I'm happy with that. On the other hand, when the algorithm is punished more for any one single error, then the system have to find those really accurate boundaries to separate it to class. Therefore, it's a low bias, high variance, and result in overfitting. So you can actually run those examples using this to see using different parameters. So this is first one is the cost parameter, and second one is the gamma. And you can compare the training result and the test result. So here we can start with 1. So gamma we set to be 0, 1. We train this model, and then we score it using this model to predict the training example. See, we allow some errors, so therefore the training wasn't 100% accurate, which is good. And the score, the test is a bit lower, so which is not bad, not too bad. But if we keep the cost to be the same and we increase gamma by tenfold, what do you predict? So when gamma is increased, the mountain is edgy. It bends itself to fit the data. So therefore, we will have so you can see the training example is almost 100%. I think I did not set the seeds, so there is a little bit of variation, but it's okay. We can still see the general trends. But when we score on the test example, we can see the performance is lower. It's lower than the other model that we have here. So you can repeat those and to verify what I had in the slides were actually happening here to understand the concept of bias and variance and the overfitting and underfitting, and how setting different hyperparameters like cos and gamma are going to affect your performance. Okay, I think that's it for the R exercise, the R demo on police shooting data.